Hello everybody, welcome back. This is Abhilash here. Welcome to BYJU'S. We are continuing with our previous year 2020 NEET questions, and physical chemistry part 2 is what we are going to get into. We have already seen some questions. I've already told you in the previous session. If you have not already watched it, I would suggest that you start from the inorganic part 1, go to inorganic part 2, then come to physical part 1, and finally reach here if you have not already watched the others. Anyways, they are all independent because these are all different questions from NEET 2020, so it won't be a big deal. But yeah, point is that it would be nice if you watch all of them, and whatever doubts you have and all, just comment there, we'll get back to you. Right, we will be able to go through it and we'll clear it up for you. Other than that, okay, so what have we already done in the previous session of physical chemistry? We had seen 7 questions, right? So we had already seen some 7 questions from physical. From NEET 2020, there were 15 questions in all from physical, organic and inorganic, 45 questions. We have already seen 7, so we'll see the remaining 8 today. Same is the approach that we have, like whatever questions we have to discuss, we will of course discuss the question and the specific answer, but I'll also give a little bit of background information about the concepts that are involved, so that whatever you are seeing, even if you have not studied it much, even if it's not very clear to you, at least you will get a decent enough idea how to approach such kind of questions, right? So yeah, let's go to the question now. Okay, let's look at the next question now. Let's read what it says, right? So the freezing point depression constant, or what you call as the cryoscopic constant Kf of benzene, is given to us as 5.12 Kelvin kilogram per mole. The freezing point depression for the solution of molality 0.078 molal containing a non-electrolyte solute in benzene, rounded off up to 2 decimal places, is. Right, so what is happening here? This is obviously options are given to us: 0.8 Kelvin, 0.4 Kelvin, 0.6 Kelvin, 0.2 Kelvin. Right, now let's see what is happening here. We are trying to see the depression in freezing point. As I promised you, we will be looking at the answer and also the relevant theory associated with it. Right, so what is depression point free? What is freezing point in the first place? Freezing point is that place where liquid converts to solid, right? So why does this happen? We say that this is that place where your freezing point is that particular place where your vapor pressure of solid will be equal to the vapor pressure, right? Vapor pressure of the liquid, right? So vapor pressure of liquid equal to vapor pressure of solid phase. That is where we say that freezing point is there, right? So when we look at the phase diagrams, we see that what happens on adding a solute into a pure, you have a solvent, it's a pure liquid, you add a solute into it, you can understand that the presence of the solute reduces the surface area available to the liquid, right, to evaporate and all. So we see that there is a depression in vapor pressure, right? So there is a reduction in vapor pressure that happens because of the presence of solute particles in a solution, right? So as far as your solution is concerned, it will have relatively lower vapor pressure compared to your pure solvent. So obviously, in order to attain a low vapor pressure, right? So when we look at the graphs, the the graphs related to different phases under one particular temperature, we will be understanding this even better, right? So yeah, the solution will freeze when its vapor pressure becomes equal to the vapor pressure of pure solvent, right? So if the liquid and the solid at some point, at some temperature, has the same vapor pressure, we say that we are at the freezing point, right? So what is Raoult's law? Raoult's law says that when a non-volatile solute is added, we know that the vapor pressure reduces, right? So relative lowering of vapor pressure is another colligative property that we study, right? So depression in freezing point, elevation in boiling point, all of these are also what you call as colligative properties, or the properties that depends upon the number of particles dissolved in the solvent, not like how many moles of original substance did I take. No, it depends on the number of particles that are there, right? So if you, like for example, take an ionic substance, the cation and anion separates out and they will be counted as separate entities. So a 1 molal solution, right, 1 molal let's say NaCl solution for that matter. So if you take 1 mole of NaCl per kg of solvent, you're actually getting 1 mole Na plus 1 mole Cl minus. So it is actually 2 molal with respect to colligative properties, right? So this is colligative properties. Continuing, so what we say is that when a non-volatile solid is added to solvent, its vapor pressure decreases. This becomes equal to, I mean, that reduced vapor pressure should become equal to that of your solid solvent, and that is the place where we call as your freezing point, right? So this is our phase diagram that I was talking about. So a frozen solvent exists in these conditions. Try to understand what is happening here. Above this, below this and all, what will happen? Think about this. So this is at one particular different temperatures, different vapor pressure will be there. You can see that on increasing the temperature, if I'm going towards the right, your vapor pressure is going up, which is naturally expected, right? So if you further increase the temperature beyond a point, it will not remain in the frozen solvent form, it will convert into the liquid solvent, right? So in the liquid solvent, you are seeing again the same thing is happening. On increasing temperature, vapor pressure is supposed to increase. This is exactly what is happening. But the point is, your solution will have relatively slightly lower vapor pressure for the same temperature, right? So if I'm taking any particular okay, so this is the original freezing point that was there. The liquid and frozen solvent having the same vapor pressure. This was the original freezing point, which is written as T0F. Now, as far as any particular temperature is concerned, let's say I'm looking at this particular temperature, some T, right? At that temperature, if I'm looking at the solution, what we are saying is that there will be a reduction in vapor pressure. So this is where the vapor pressure is going to be for your solution. The upper dot is for solvent and the lower dot is for solution, right? So if I keep plotting the vapor pressure for different temperatures, I'll keep getting different line, right, instead of the upper line. I don't want to draw it much more here because we will be seeing that in the next frame, right? So this is the solution vapor pressure. You can see at a particular temperature, vapor pressure is lowered, right? So this is the reduction in vapor pressure. Oh, of course, my straight line is way too straight. Yeah, so this is the reduction in vapor pressure that we are seeing. And what you can understand is, freezing is still defined in the same way. The place where the solid and the pure solid solvent and the liquid, whatever form it is in, solvent or solution form, wherever their vapor pressures become equal, that is the freezing point. So obviously you can see for the pure liquid, I had my freezing point as this. But for your solution, this is what I'm getting as the new freezing point. There is a reduction in freezing point, which we call as the depression in freezing point. What was observed is that delta TF is proportional to the molality, right? So T0 minus TF. T0 is what? The original freezing point. TF is what? The new freezing point of the solution. Delta TF is the depression, and that is equal to T0 minus T, right? So this depression is seen to be proportional to molality. This is the idea, right? So in order to remove proportionality, what do? We multiply by a constant, which is called your cryoscopic constant or freezing point constant, right? So yeah, delta TF is equal to KF into molality. This is our equation. Simple equation, simple. I mean, NEET doesn't like ask you too many complex things and all. Very simple, direct formula based question is what we have in hand here. So the thing is, delta TF is asked. We have been given the value of KF and we have also been given the value of molality, right? So the thing here is that molality, what should I take? Like for example, when I told you the NaCl example, I told you molality will be directly double. If I had something like MgCl2, molality will be triple, right? 1 molal, molarity, all of these, right? So molality is what we are taking here. So let me speak in terms of molality. So molality, if I have 1 molal MgCl2, what does that mean? 1 mole MgCl2 in 1 kg water, right? 1 kg solvent. So 1 mole MgCl2 will give me 1 mole Mg2 plus and 2 moles of Cl minus in solution, right? So I'll say that, okay, the total molality, actual particles per kg of solvent is not 1, it is 3, right? So here in this question though, there is a thing that our molality given to us was 0.078 molal, and should I be considering something like this NaCl thing here? No data is given. That is also one thing, but another statement is given to us. It's a non-electrolyte. What do you mean by non-electrolyte? Something that doesn't split up into ions in solution, right? So electrolytes conduct electricity in solution phase or in molten phase because they break down into constituent ions and they will be able to travel. But here we had a non-electrolyte, so 0.078 molal is going to be the number of particles, like, for example, glucose, right? So if you have 1 mole glucose, it is 1 mole glucose only. It is not going to split up into ions. Same story here. 0.078 molal was the original molality of the solution. That is exactly what we will take as well, because it is non-electrolyte. And Kf is also given. So the obvious thing is that we can calculate delta Tf to be equal to 5.12 Kelvin kilogram per mole into molality is mole per kg. So obviously mole per kg per mole will cancel out and only Kelvin will remain. 5.12 into 0.078. This is what we are looking at. Approximate answer is what was anyways asked, so we can easily do the calculation. Obviously nobody expects you to be an accountant, you are going to be a doctor, so obviously don't sit and multiply 0.078, I mean 78 into 512 and then you are like, okay, this is not happening. Don't do that. Instead approximate. See, all the answers were like decently far away, no, 0.1, 0.2, 0.3, 0.4, something like this. So obviously approximation is something that we can do. So this 0.078 is almost 0.08, right? So almost 0.08, and this 5.12 is almost 5, right? So what did I do? I increased one, I decreased the other one. Probably they would have, I mean, obviously I'm making an error in calculation, but one error was increasing my answer, one error was decreasing my answer. Probably it is going to bring my answer closer to the actual answer. Looking at this, it is very easy to see 5 into 0.08 is 0.4 Kelvin, right? So one I decreased, one I slightly increased, and I got 0.4, and I'm happy with this. This was one of the answers, so I'm hoping this is the one, right? So yeah, so what are we finding here? We are using the formula delta Tf is equal to Kf into molality. Kf was given to us, molality was also given to us. Obviously we calculated the value of delta Tf, right? So what did we get? We took 5.12, we took 0.078. Instead, we took it approximately as 5 and 0.08, and we got the value to be equal to 0.4, right? So looking at the question, it said that the molality is known, the Kf value is known, and what is the answer? What is the depression in freezing point? That was what was asked, and obviously our answer was 0.4, which is B option. Okay, now let's look at the next question. It's an interesting question from electrochemistry. Simple question, but yeah, I mean something that you have to be very much clear about if you are looking at the basics, right? So yeah, the question says on electrolysis of dilute sulfuric acid using platinum electrodes, neutral electrodes, the product obtained at the anode will be, right? So gases are given to us: oxygen, hydrogen sulfide, sulfur dioxide, and hydrogen gas, right? So going forward, yeah, so just based on the fact that this is anode and this is where oxidation is taking place, it should be possible to find out the answer without doing anything else, because the other options probably will not be able to give you the right answer. Sulfur dioxide, think about this. You had originally dilute sulfuric acid where sulfur was in +6 oxidation state. Will you get sulfur dioxide at anode? Obviously anode is where oxidation takes place, right? And cathode is where reduction takes place. So there is no chance that you would have got H2S either. H2S is where sulfur is in -2 oxidation state. Sulfur dioxide is where it is in +4 oxidation state. So these two are not possible. Hydrogen, how can you get hydrogen? H+ to H2 conversion is what happens, right? H+ to H2 is also reduction. So none of these are possible. There is only one answer. That was one trick. But yeah, let's see. What is electrolysis? As the name itself suggests, electrolysis, right? So you are forcing a dissociation kind of, breaking kind of reaction, which is not spontaneously something that happens on its own. We are using electricity to cause this lysis, right? So we are giving energy, we are spending energy in the form of electrical energy to force this, what you can call as a non-spontaneous reaction to take place, right? So the process of using an electric current to bring about a chemical change is what we call as our electrolysis, right? So electrolysis is a process of oxidation and reduction, of course. It is a redox reaction that we are carrying out. In one compartment, anodic compartment, you will be having oxidation. In the other, cathodic compartment, you will be having reduction. Standard definition, plus minus and all, don't worry. Always remember this. Anode is where oxidation takes place, cathode is where reduction takes place. So electrolysis is the process of reduction and oxidation due to the current in the electrolytic solution. So what is an electrolyte? Something that will conduct electricity in solution or molten phase, mostly ionic substances, right? So you take electrolytic solution, you insert platinum electrodes, and you have taken the electrolyte. In our particular case here is dilute sulfuric acid, right? So pure water has very low concentration of H plus and OH minus, of the order of 10 to the power minus 7 molar. So it won't be a very good conductor. But if you add some dilute H2SO4, H2SO4 is a decently strong acid, right? So you will be having H plus, you will be having SO4 2 minus in solution. The presence of ions makes this a decent conductor, right? So yeah, anode, as I was telling you, is where oxidation takes place, and cathode is where reduction takes place. Now, what exactly is happening in electrolysis process? As I told you, the electrodes are ready to supply electricity, right? So electrodes are ready to give you electrons and take away electrons from you as well. Where it gives electron, it is supplying electron to something. So that is where reduction takes place. Where it is pulling away electrons from you, removal of electron is happening from something, that is where oxidation is taking place, right? So what will happen as far as our cathodic compartment is concerned? In your cathode, which is where reduction takes place, you can obviously understand there is no competition angle, right? So you have, what do you have in your solution? You have H plus ions, you have SO4 2 minus ions, little bit of H plus coming from water, little bit of OH minus coming from your water as well, right? So H2O is also there. H2 by itself is a thing that can get oxidized as well as reduced as well. So these are the different things. So when you have electrolysis, normally let's say if you are doing electrolysis using molten NaCl, let's say, so you have Na plus and Cl minus as the only two ions. So there is only possibility of reduction of Na plus, only possibility of oxidation of Cl minus. So there is no ambiguity, there is no competition between ions there. Competition will be there if you have some situation like this where more than one ions, more than one species are present, which can get both oxidized, reduced, right? So as far as cathode is concerned, it is where reduction takes place, and reduction, H plus is available, right? If H plus was in very low quantity, maybe even we can think H2O itself will start to dissociate and you will be getting hydrogen from there. But yeah, H plus is available. We are using dilute sulfuric acid, 2H plus plus 2 electron giving you H2 gas. E naught value is 0 volt. We know this is standard reduction potential, right? So this is going to happen at your cathode. But our question is not cathode, it is anode, right? So when I'm looking at the anodic compartment, this is where oxidation takes place. There are two things that can get oxidized. Your H2O, which is there in the solution, can get oxidized into oxygen. H2O is where oxygen is in -2. O2 gas is where oxygen is in 0. So yeah, -2 to 0 oxidation is taking place. Then another possibility is SO4 2 minus, right? Now SO4 2 minus giving you H2OA 2 minus. This is interesting. Here oxidation is not taking place of sulfur. Sulfur is already in its +6 oxidation state in sulfate. So there is no way that it can go beyond +6. The maximum oxidation state of any element is equal to its number of electrons in its valence shell, right? I mean, let's just say at least non-metals and all, this is very clear. So in your sulfur, you have 6 electrons, right, in the valence shell, 16th group element. So you will be seeing a maximum oxidation state of 6. So obviously it is not going to go beyond this. So what is happening is you have your oxygen, which is all in -2 state, which can get converted into oxygen that is present in H2OA 2 minus. Now this is where you have your peroxy linkage, right? So you have your H2OA 2 minus that looks something like this, right? So you have your H2OA 2 minus, which is having a peroxy linkage where the two oxygen atoms are in -1. So originally all of the oxygen atoms were in -2 in sulfate, but there are two oxygen atoms that are in -1 right now, which means -2 to -1 increment in oxidation state. Oxidation has happened to oxygen atoms here, right? Not sulfur, be very clear. But the point is that as far as these their SRP values are concerned, right? So you will see that okay, depending upon the SRP values or standard oxidation potential values. See, SRP, standard reduction potential, standard oxidation potential, they are plus minus of each other, right? So the E naught given here, without saying that this is reduction potential, this is basically E naught of this particular reaction that is given. Oxidation potential of H2O to O2 is what is given to us as minus 1.23. And as far as sulfate is concerned, oxidation potential to your H2O2 minus, E naught is given as minus 1.96. Now, whichever has a higher potential is said to have a higher ability of that reaction to take place, right? So whenever you have potentials, always think of them as the ability of a reaction to take place. Higher the potential, higher will be the ability of that particular reaction to take place. So looking at this, it looks as if 1.96 is larger, but it is in negative, right? So minus 1.23 is actually larger than minus 1.96. So whichever has a higher potential to take place will take place, right? Sulfate is in dilute concentration, right? So dilute sulfuric acid is what we had. So sulfate isn't in much high concentration. When you have dilute solution, H2O will be the one that gets oxidized and we will be getting oxygen. On the other hand, if I increase the concentration of sulfuric acid, it is possible that at some point in time, even though the oxidation potential is lower, you might be seeing that this is the reaction that takes place predominantly because of the oversupply of your sulfate ions, right? So at dilute concentrations, oxygen is formed at anode, and at high concentrations of acid, H2O2 minus is what is obtained at the anode, right? So we were already asked what is a gas. So obviously H2O2 minus is not a gas, and this is not going to be the answer for us. Obviously our answer is oxygen here, right? So what exactly is happening at the anode? We are seeing oxygen gas liberated. What is happening at the cathode? Hydrogen gas is liberated. This is the experimental setup of sort what is there, right? So we have put a slightly higher potential. You might have seen minus 1.230, right? So if I see I need a higher potential than that, basically we have applied basically we have set this up. There are two electrodes. You can see there is a negative side which is on this side and positive side. Negative side means supply of electrons. This is where reduction will take place. So this is where your hydrogen gas is formed, right? And as far as positive side is concerned, obviously positive electrode is where electron will be pulled out. So obviously that is where oxidation is taking place. This is where we end up getting our oxygen gas. One more interesting observation that you have probably can see here is the volumes. Compare this. Suddenly see this. This is the volume of oxygen and this was the volume of hydrogen. Why? Because the net reaction that is actually happening here is 2H2O giving us 2H2 plus O2. So hydrogen and oxygen are produced in 2:1 mole ratio. So you can see here that the volume of hydrogen is also double of oxygen, right? Not a part of the question, but just an interesting observation nonetheless, right? So going forward in this question, what was asked? We were told, okay, electrolysis of dilute sulfuric acid is taking place. Tell me what is formed at the anode. So anode is where oxidation takes place and anode is where oxygen gas is formed in this particular reaction. So our correct answer is A option. Okay, let's go to the next question now. What does it say? It says, measuring the zeta potential is useful in determining which property of a colloidal solution, right? So this is about colloids, surface chemistry chapter, specifically within that colloids. Colloidal solutions, we know what they are. It's not exactly what you call as a true solution. This is something that shows Tyndall effect and all. We know larger size particles, right? Nano to micro level particles, aggregation of particles of salt, or which have like charges on them, right? So they have charges on them, and these charges is what stabilizes the solution. These are like relatively heavier, larger aggregate particles. They should have probably settled down like what happens in sand. Like let's say you take a sand and you mix some water and you shake it up. It looks like brownish for a while, but then it settles down. Colloids don't settle down. Colloids don't settle down because they have charges and they are stabilized. If you diffuse this charge one way or the other, use some other electrolyte and discharge it, then obviously it will settle down. But otherwise, these are substances which are stabilized because of the charges that are there on the spheres. So based on that stabilization, I guess you have already guessed the answer. But yeah, let's read up more about this zeta potential and what exactly is this thing and what exactly does it represent, right? So what exactly is a Helmholtz double layer and zeta potential is what we are going to look at now, right? So colloidal particles, as I was telling you, they always carry charges, and the charge and the presence of charge and their repulsion from each other because of these charges is what causes a colloid to be stable, right? So the charge on small particles is due to the electron capture. I mean, there can be electron capture that is happening due to preferential adsorption of ions from solution. Like common ion might get adsorbed. There might be something like, let's say for example, AgI, Ag, or AgI I minus kind of salt. What you see is that, okay, AgI is supposed to be a precipitate, so there is a sizable chunk that has almost on a what you call as colloidal range if they have a size, and then they pick up a common ion, right? Let's say if it picks up I minus on it, AgI I minus will be a negatively charged salt. On the other hand, if I have a AgI Ag plus, let's say I have lot of AgNO3 and I slowly add Ki into it, so lot of AgNO3 is there, lot of Ag plus NO3 minus. AgNO3 is soluble, AgI is not, right? AgI has this yellowish. So if you add some Ki, immediately AgI will be found. AgI is supposed to precipitate, so it is up. They will collect up. They will be in solid state. They will be in your aggregated state, not in solution phase. They are going to deposit, but there are a lot of Ag plus around it. So Ag plus will get adsorbed on its surface, and then you end up getting AgI / Ag plus colloid, which is positively charged, right? So depending upon what is there in excess, AgNO3 was there originally in excess, I'll get Ag plus AgI kind of salt. If Ki solution was there in excess and I slowly add AgNO3, what will happen? Ag plus is not there. AgNO3 I am adding. Ag plus AgI will form BPT. The expectation is that, and they start to make your colloidal size particles, and there is no Ag plus around it. I am the one who is adding AgNO3. There is no more Ag plus, but there are I minus all around, right? Ki solution, you are adding AgNO3. So there are a lot of I minus. They will get adsorbed on the surface of AgI aggregates, and you will get your negatively charged salt also, right? So yeah, preferential adsorption of ions is something that creates salts due to the formulation of the electrical double layer. This is the topic that we are coming to, right? So when two or more ions are present in the dispersion medium, what we see is the preferential adsorption. So dispersion medium and dispersed phase, I'm sure you know, whatever is like forming this colloid thingy, that is your dispersed phase, and your dispersion medium is that thing in which you are making your colloid, right? So preferential adsorption of the ion common to the common ion colloid to the colloidal substance. This is what usually takes place, and this leads to an what you call as your double layer, electric double layer. We'll come to that. Having acquired a positive or negative charge by selective adsorption on the surface, as stated, what we end up seeing is, what do we see after this? This layer attracts counter ions. I mean, obviously we know opposite ions attract, right? So there is a counter ion, as in the oppositely charged ions, which gets from the medium, it gets stuck on the surface as well, right? So it forms a second layer on top. The combination of these two layers of opposite charges is what you call as your electrical double layer, right? Now we speak of something called as the fixed layer and something called as the diffuse layer. As the name itself suggests, fixed layer is something which is more let's say permanently attached to the colloid, colloidal size particle, and the diffuse layer is something which is more mobile, which is more free to move about kind of ions. The first layer on the double layer is firmly held and is called the fixed layer. We'll see an image also, it will get more clear. The second layer on the double layer is mobile. It is relatively free to move. Obviously you can understand, right? So if you have a cation, and let's say even a dipole like water is surrounding it, right? So the layer closest to the cation will be the one most attracted to the cation. So they are bound to have relatively higher attraction to this cation. So they are relatively less mobile, right? So I'm just drawing a parallel. This is not what is happening in colloid. We'll see what is there. But the idea is this, that the first layer that is there around is very rigidly held relatively, at least compared to the other ions, which are, as you go further and further away from the charge, the sphere of influence is reducing, they are going further away, less attraction, so they will become more mobile as you go outward, right? So the second layer is what we are calling as the mobile phase. The potential difference between these two, right? So one is positive, one is negative, or one is negative, one is positive. The potential difference between these two is what you call as the zeta potential or the electrokinetic potential, and higher is this value, more will be the stabilization. See what is happening here. So you have all the negative charges that are there. This is the surface negative charge that is there. On top of that, there are a lot of positively charged ions that have come and stuck on it, right? That is what you call as your fixed layer, right? Going further, so the surface charges are there, oppositely charged ions that are like more rigidly held by this surface charges are there, that is your fixed layer. Beyond that, you have your diffuse layer. So you can see there, I mean, it's not like one particular set of charges that are shown. That's because they are more mobile. There can be other ions also, right? Positive and negative ions also could be there because they are free to move. Nobody is stopping there. The others on the fixed layer that I shown, you can see here in the image that all of them are exactly of the same charge. I am not very sure this yellow is visible, but I hope this will be visible now. So this yellow, there is no negative charge I have drawn here. Why? Because it's a fixed layer that is there, so they are very strongly held here, and beyond that there is less attraction. Beyond that sphere, beyond that layer, there is less attraction, which we call as the diffuse layer. The potential difference between these two layers is what you call as your zeta potential. So you have your colloid, around that you have your Helmholtz double layer. The Helmholtz double layer, the potential difference between them, the layers, is what you call as zeta potential. The electric double layer is responsible for the stabilization. Obviously you can understand, this is what is causing these ions to be these colloidal size particles not to come and ram into each other and like settle down as a PPT, because they are opposite, they are all of the same charges, they are going to repel. This is what leads to stabilization in your colloid, right? So the repulsive forces between the charged particles having the same charge prevent them from aggregating and prevent them from coagulating or settling down. So looking at the question, what do you see here? The measuring zeta potential is useful to determine which property of your colloidal solution. It is reading the options: solubility, stability of colloidal particles, size of colloidal particles, and viscosity. Obviously you can see that B is the correct answer. Stability is what is most accurately determined by your zeta potential and your electric double layer. So our correct answer is B option. Okay, now let's go to the next question. So what does this say? Let's read. It says, for the reaction 2Cl giving us Cl2, the correct option is, right? So 2Cl in gas phase is getting, so atomic chlorine, 2 moles are getting converted into 1 mole of chlorine molecules. We are supposed to speak about the enthalpy in this reaction and also the entropy change in this reaction. So enthalpy change and entropy change. So what is enthalpy? Enthalpy is a measure of the heat associated, right? So delta H turns out to be equal to heat under constant pressure, QP. I'm sure you have remembered this. The point is that most of the reactions that we do in a lab and all, if you're like pouring, let's say, HCl and NaOH in a test tube together, it is open to atmosphere. It is at 1 atmosphere external pressure. The pressure over the surface will be 1 atmosphere. This is a constant pressure process, isobaric process. The heat of an isobaric process, QP, is equal to delta H, right? So H is equal to U plus PV. This is the definition. We won't go into much details here. It's not relevant. But yeah, point is that from here, when you write DH is equal to DU plus PDV plus VDP, then you could write DU plus PDV to be equal to DQ, and VDP will be 0 if pressure is not changing. So we can say that DH will be equal to DQ under constant pressure, right? So yeah, so DH is equal to DU plus PDV plus VDP is what is written here. So we can see that, okay, VDP will be 0 if pressure is constant. So we know that VDP is 0. Then what is remaining? DU plus PDV. But what is PDV? We know that minus PDV will be equal to dW, right? So du minus dW. So du minus dW from first law is your dQ, right? So we are getting dH is equal to dQ plus VdP. Constant pressure means that your constant pressure means that dP will be 0. So we know that dH is equal to heat under constant pressure, right? So enthalpy is a measure of heat content of a system. Exact value of enthalpy cannot be calculated. We can calculate delta H. Delta H is NCP delta T. If you are looking at a particular gas or some substance undergoing no reaction, right? So no phase change, no reaction, NCP delta T is going to be the delta H, right? So what is endothermic and exothermic? Something that absorbs heat is called endothermic, where your delta H turns out to be positive, right? Endothermic is when delta H is positive. Heat convention, right? So heat absorbed is positive in chemistry, heat given out is negative. So endothermic reaction, delta H is positive. Exothermic reaction, your delta H is going to be negative, right? Photosynthesis, when heat is used by the plant to make something. So at that point in time, you say that, okay, this is the endothermic process, it's absorbing energy. Combustion is where you are releasing a lot of energy, heat is released, so it is a exothermic process, right? So what do we see? Enthalpy of your products minus enthalpy of your summation, I mean all the products combined, enthalpy of products minus enthalpy of reactants is what you call as delta H. So in an exothermic process, what can you say? Delta H is negative. Delta H is negative means enthalpy of products should be less than enthalpy of reactants, and this is what we see. Product has a lower enthalpy compared to your reactant. Going forward, the difference between these is what we will call as heat of reaction or delta H of reaction. On the other hand, if I have a, endothermic, yeah, so as we were saying, negative will be the value of your delta H if your process is exothermic, where the product is having a lower enthalpy compared to your reactant, right? So heat flows from system to surroundings. In an endothermic process, other way around, you can say, okay, final enthalpy should be more, that is why it is absorbing heat in the process. So reactants have a lower enthalpy, products have a higher enthalpy. The difference between them is heat of reaction or delta H, which is positive. This is endothermic reaction, right? So we will discuss basic details about all of these. I'm pretty sure you already know this, but still, right? So sign convention, yeah, as we were saying, delta H will be positive in an endothermic process. Now coming to our process, what is happening here? You have chlorine atoms converted into chlorine molecule. So this is bond formation, right? Bond formation is when energy is released. In order to break a bond, if I'm looking at the reverse reaction, I would have had to give what you call as your bond enthalpy, energy equivalent to bond enthalpy for it to break down. Here bond is formed, so this is going to release energy. How much energy will be released? Bond dissociation energy of ClCl, right? So this will be the energy that is released. So I can write delta H will be equal to minus bond dissociation energy of ClCl. Whatever energy is needed to break ClCl, negative of that will be the enthalpy here. Energy is released here, right? So you can say here that the enthalpy of this reaction has to be negative. The second part is the entropy part. So what is entropy? Entropy S is a measure of randomness of the system. A more random system is said to have higher entropy, and nature, by this is the observation in nature, that nature in general prefers things to get more and more chaotic, right? The entropy change has to be positive. This is the general intention. Not always. Is it always going to happen? No. We already know the condition for spontaneity, which is that delta G, which is equal to delta H minus T delta S, should turn out to be negative. That is the only criteria. If enthalpy change is negative and entropy change is positive, this is always spontaneous. If enthalpy change is negative, but your entropy change is negative, we can say that this will happen spontaneously at lower temperatures, right? So at higher temperatures, this minus T delta S will become too large that delta G will become positive. Process will get non-spontaneous. Here we are just asked about entropy, right? So this is simple, no spontaneity, nothing, that angles are not there. We just have to comment about the sign of entropy change. We can see that randomness is decreasing. Why? Because initially you had two atoms. They have more possibility of causing chaos, right? On the other hand, after you convert it into a molecule, you have a molecule Cl2, which will obviously have relatively lower entropy compared to two independent different particles. So entropy change is also negative out here. right? So what we can say is that the tendency of the system's energy to become more disordered is what you call as entropy, and increase in entropy is generally favored in a spontaneous process, but it's not compulsory. Depending upon the temperature, at times it can be spontaneous or at times it can be non-spontaneous. At high temperature, for example, this particular process would be non-spontaneous. Why? Because Cl atoms should combine and give you Cl2. This is reducing entropy, so it will happen at a lower temperature. Or think about it like this: at high temperature, Cl2 will dissociate. So just think what happens in nature. You should get your idea about entropy very clearly, right? So as your number of gas molecules increase, we can say that entropy will increase. So delta Ng greater than 0 implies there is an increase. Delta Ng, what is delta Ng? Number of moles of gas products minus number of moles of gas reactants. If it is positive, we can say entropy will increase. If it is negative, we can say that entropy will decrease, right? So this is obviously primarily related to gases that we are speaking about this. If there are solutions and all, there are other factors, mobility and all of these are there, right? So different ions have different extent of hydration in solution, they will have different speeds and their entropy would be different and all. But yeah, point is, let's stick to the question which says that 2 chlorine atoms are converted into one molecule, which means obviously delta Ng is -1, right? 1 minus 2, one product, 1 mole of gas product, 2 moles of gas reactants, -1 is your delta Ng, entropy change will be negative. Looking at the question, we can see that, okay, so chlorine bond energy released, so we can say it is exothermic, and atoms are converting into molecules, less particles are there finally, less will be entropy, so delta S is also negative, delta H is also negative. Where do I see this? Yeah, so I am seeing this in C option, which will be our final answer. Okay, now let's look at the next question. What does it say? The rate constant for a first order reaction is 4.606 into 10 to the power -3 per second. This is the standard unit. The time required to reduce 2 gram of the reactant to 0.2 grams. Simple question, formula based question. If you know the theory, it will be very nice. We will still briefly go through the theory anyways. So yeah, 200 seconds, 500 seconds, 1000, 100 seconds. All the answers are pretty nice. So it's not a tough calculation, right? So when you look at the answers, they don't look ugly. You can understand to some extent that this is going to be an easy calculation. Pick it up. Otherwise, if you see like all random numbers, 3733, root 3, won't be there. But yeah, let's say such ugly numbers are there, obviously your calculation is going to be a risky business, so you can attempt that question later on, right? Anyways, going forward, so what is the idea behind first order kinetics? So you know that the rate of the reaction is proportional to the first power of the concentration of the reactant, right? So first order, right? So in general, what do we say? Rate is supposed to be equal to minus k a to power n, right? So an nth order reaction, or let me write this as minus dA by dt, right? When I'm writing A square bracket, I'm looking at activity, concentration. So A giving product, some reaction like this is there, right? Coefficient is 1. How do I know? Rate of a reaction is supposed to be -1 by A dA by dt, right? If I had like some A coefficient was there, so -1 by A dA by dt is rate of reaction. Here I'm looking at something with a coefficient of 1, so I can write rate to be equal to minus dA by dt. This is supposed to be equal to minus Ka to power n, nth order reaction. Here we have order to be equal to 1, so I can write the minus dA by dt equal to Ka. Oh, sorry, we don't need this minus here, right? So rate is going to be equal to minus dA by dt, which will be equal to Ka to power 1. This is our first order reaction, right? So this is what you call as your differential rate law equation. You can integrate this to get the relationship between A at some point in time t and A naught, which was there at time t equal to 0. So we are going to write, okay, so instead of A, we have taken here, you can see dr, right? So minus dr by dt without square bracket. I hope you understand. it's supposed to be square bracket to say that we are looking at activity, but yeah, point is minus dr by dt is equal to k into r to power 1. This r, when I'm writing, it is actually read in your head as square bracket r because it is activity or molar concentration, right? So yeah, what can I do? I'll bring r here and take dt to the other side. So we'll get my dr by r is equal to minus k dt. Integration of dr by r, integration of dx by x is ln x, right? So we'll get ln r is equal to minus kt plus I. What do you mean by this I? This is the constant of integration, right? So if you have what you call as a indefinite integration where there is no limits, upper lower limit, then we say that okay, this is the indefinite integration. There is supposed to be a constant of integration here. You take different at t equal to 0, we know that r is some r naught, and at time t equal to t, r is some other r, right? So I am getting ln r naught to be equal to I. What did we do here? In the previous slide, we to put t equal to 0. So minus k into 0 is 0, and ln r naught will be equal to I. So from here we got the value of I from the initial condition, and at some other time t, this is the equation that we have. So instead of I, basically I can write ln r naught. This is the idea, right? Ln a naught if you are taking a. Right? So going forward, substituting this I into this equation, we are getting ln r is equal to minus kt plus ln r naught, right? So what will I do? I'll take either I'll bring this to this side and take this to the other side, or I can bring this to this side, and this is the equation that I'll get. Ln r minus ln r naught is equal to minus kt, or ln r naught by r is equal to kt. Right? So yeah, what am I getting? Minus kt equal to, see, ln a minus ln b, you have to remember this. The relationship in logarithm is ln a by b, right? So, or even in log also same thing, log a minus log b is log a by b. So ln r minus ln r naught is ln r upon r naught. This is the concentration of reactant at time t, and time t equal to 0. So k will be equal to 1 by t ln r naught by r, right? How did we get this? When we reverse this first one, ln r upon r naught, we will get minus ln r naught by r, minus minus we cancel, and we get k is equal to 1 by t ln r naught by r. This is written here because this is an important equation to remember. Analysis of first order kinetics. Many times you are given the value of t, you are given the value of r and r naught, and they will ask you to find k. Many times this also happens. That is why this equation is also given. What is our question? Our question is about time. So time will be equal to 1 by k ln r naught by r. Right? So do we know r naught? Do we know r? Yes, we know all of these, right? So this was given to be some 2, and this was given to be some 0.2. This was what was asked, and this was given to us as 4.606 into 10 to the power minus 3. Right? Substitute the values. Very easy calculation, right? So one more thing is there. I'm sure you know this. The thing is that, okay, it is already written here. You might have noticed. Instead of ln x is 2.303 times log x. So we converted that ln r naught by r into 2.303 log r naught by r. Why? You will see very soon. Right? So the k was given to be a beautiful number that can easily be used here. That is why, right? So I am getting t equal to 2.303 by k into r naught by r log of this thingy, right? Substituting the value, what are we going to get? K is equal to 4.6 into 10 to the power minus 3. So what will you get? Yeah, r naught. I mean, activity. It could be in terms of concentration. It could be in terms of number of moles, it could be in terms of pressure of gases, it could be in terms of volume of gases at same pressure, it could be just about anything. R naught and R, just keep the same thing, right? One place you take pressure, other place you take mole, don't do that, right? So whatever it was given to you, whatever property was given to you, just use that initial. If it was molarity, I'll take initial molarity and molarity at time t. So yeah, R in general is the reactant representation of the reactant, whatever be it, right? Going forward, substituting these values, what will you get? 2.303 by 4.606. You understand why we converted that. 10 to the power minus 3 and log of 2 by 0.2. 2 by 0.2 is 10 and log 10 is 1, right? So this whole thing is not of our concern. Now 2.303 into 2 is 4.606, right? And if this 10 to the power minus 3, if it goes to the numerator, it will become 10 to the power plus 3. 1 by 10 to the power x is 10 to the power minus x, right? So 1 by 10 to the power minus 3 will be 10 to the power plus 3, right? So 10 to the power 3 divided by 2 or 1000 by 2, which is equal to 500, right? Beautiful answer. Very simple calculation is what we are seeing. So what we got is that T will be equal to 1000 by 2 into log 10, right? So this is obviously 1. We can say this answer will be 1000 by 2, which is 500 seconds, right? Second inverse was what was there in our K. You might be remembering, right? So in this we had second inverse. When it goes to the numerator, it will become positive 1. So second, 500 second is our final answer. Looking at the options here, where is our correct answer? It is of course option B. Okay, now let's look at the next question. So the next question says the number of protons, neutrons and electrons in lutetium 71, 175 respectively are. Simple question. Atomic structure, the one of the first things that you do in atomic structure, where the layout, the representation of a atom or an element is given, and then you are explained what are these individual numbers, right? So yeah, so what is asked is protons, neutrons and electrons respectively. Protons, electrons will obviously be same. Neutrons will be different. Based on that also at times you will be able to solve. Yeah, here I can solve just using this also information. But yeah, let's go forward, right? Let's not use any tricks. So yeah, what is the general idea when you are looking at the representation of an atom? In general, we say X, Z and A, right? What is this X? X is the symbol. A is the mass number, which is number of neutrons plus number of protons, and Z is your atomic number, which is actually number of protons, right? So what did we have here? We had lutetium, right? So lutetium 71 and 175 is what was given to us. So number of protons is same as atomic number, which is 71. Number of neutrons will be atomic mass number minus atomic number. So 175 minus 71 is what? 104, right? Easy calculation, right? Electrons will be same as if there is any charge, then yeah, we would have had to subtract the charge because minus charge would mean more electrons. So number of atomic number plus that magnitude of charge will give us number of electrons. But yeah, here we have a neutral atom, so it is not there. So this is 0. So atomic number is 71. So yeah, simple calculation, right? Simple questions are there. A lot of simple questions will always be there. In NEET, never be too tensed about calculations or like tough questions and all. It will always be in low numbers, right? So yeah, what is our atomic number? 71. So number of protons is 71. What is our mass number? It was 175. So 175 minus 71 is going to give us 104 as the number of neutrons. Electrons will be same as the number of protons because we are looking at a neutral atom here. So that will also be 71. So what was our answer here, right? So let's look. Anyways, I told you electrons, protons had to be same. In all of these, you can see that is violated, right? 104, 71 in A, 71, 104 in B, 175 and 71 in C. Only D option had 71 and 71 and 104, which is of course our correct answer. Okay, let's continue. Let's go to the next question. What does it say? Let's read. An increase in the concentration of reactant of a reaction leads to a change in, right? Simple question, conceptual question, right? So, does it change the heat of reaction? Does it change the threshold energy of the reaction? Does it change the collision frequency in the reaction? Does it change the activation energy? So for this, we have to understand these terms and how they are related to the amount of substance, right? So we will directly go to discussion about the answer as well. But let me briefly, just quickly explain this, right? So heat of reaction, right? Of course, when you write some A plus B giving you C plus D, this has a fixed heat of reaction that we speak about, right? So some X kilojoule per mole is the reaction enthalpy, right? Obviously, that is not going to change if you have your reactant, more reactant, less reactant and all, right? It is obvious. This is a standard value that is given, right? Enthalpy of combustion of carbon. Does it matter if you have carbon or not? That is a fixed value, right? So enthalpy of reaction or heat of reaction is not going to change. Threshold energy. What is threshold energy? We know the energy profile diagram that we come across. Reactants are at some energy. Let's say we have an exothermic reaction where products are at an even lower energy, and let's say this is how the energy is changed, right? So what happens is that obviously reactant is not sitting, reactant is stable, it is a stable compound, which means that it is sitting, right? It's not like explosive that it will immediately just go directly to products, right? Directly go on reducing its energy. No, you will have to give some activation energy, that extra energy that is given to the electrons, the substances, reactants, so that probably, let's say that this a chemical reaction can in general be represented as breaking of old bonds and forming of new bonds, right? So obviously the old bonds have to break first. This is a stable substance, this is existing. You have to break the bonds first, so that then now they can form new bonds, right? So that upfront some energy has to be given for the reaction to kick up, right? Kickstart, right? So obviously that energy, that extra energy that we are providing is what we call as energy of activation, EA, right? So obviously energy of activation also has a previously defined value. Unless and until I am changing temperatures of the whole system, energy of activation has a predefined value. The threshold energy, the energy carried by the substances that is about to react, is what you call, that can convert into products, is the threshold energy. Obviously I am not going to change threshold energy just by adding some reactants, right? So the energy that they should carry for them to convert into products is what you call as threshold energy. I'm not changing that just by adding reactants, right? I'm obviously not going to be able to affect that. Activation energy is also not affected, threshold energy is also not affected, heat is also not affected. Obviously collision frequency had to be the answer. Think about this, what is happening, what is collision frequency, right? So the idea is that, as the name itself suggests, how frequently are collisions taking place. Number of collisions happening per unit time, per unit volume is what we call as collision frequency. Obviously, when I have, let's say, let's say these are the different molecules that are there, right? And these are different type of molecules, and they are supposed to collide and react and stuff, right? They will have certain number of collisions happening right now, right? If I increase the number of let's say reactants, right, I increase the numbers of both, obviously you can understand that the number of collisions will increase, the number of particles per unit volume is increasing, the number of collisions will increase, the reaction rate is going to go up, right? So what happens is that molecules are always in constant motion, they might be colliding against each other. Not all collisions have sufficient energy for a reaction to be carried out, right? So at times the collision just will happen, they will go their own separate ways, right? But if they have sufficient energy where collision can lead to a situation where the molecules have threshold energy, activation of this reactant into its that intermediate state is happening, and from there products can be formed. So we say that if I'm increasing the number of particles, the number of collisions will increase, number of effective collisions will also increase, reaction rate will go up and all, right? So with an increase in and also this is not always a compulsion, okay? There are some cases where like adding extra of your reactant might actually turn out to be an inhibiting factor. It might be that there is too much overcrowding and the molecules don't have sufficient ability to convert into products, because effective collisions are actually reducing. That can also happen, rare cases are there, but yeah, point is that if you increase the number of reactants, the number of collisions and number of effective collisions will be generally increasing. This increases the frequency of collisions because there is more crowding of particles, right? So this normally leads to an increase in the rate of reaction, right? So obviously on increasing the number of particles, the number of collisions and collision frequency is going to increase, right? So yeah, looking at the options here, what do you see? We have already discussed about this. Heat of reaction can't be changed by you. Threshold energy cannot be changed by us unless and until we change energy itself, right? We increase the, in fact, threshold energy is still something that we cannot affect directly. Changing temperature might to some extent slightly maybe vary your threshold energy, activation energy, but yeah, it doesn't affect it, right? At least just adding a reactant will not affect these. The only thing that can actually change is your collision frequency, which is option C. Okay, now let's look at the next question, right? What does it say? It says, find out the solubility of NiOH twice in a 0.1 molar NaOH solution, given that the ionic product of NiOH twice is 2 into 10 to the power minus 15. right? So this is from our ionic equilibrium or equilibrium chapter, and specifically from this part towards the end of ionic equilibrium, which is called the solubilities, right? Solubility of sparingly soluble salts. So nickel hydroxide, NiOH twice, here is a sparingly soluble salt with a very low value of Ksp 2 into 10 to the power minus 15, right? Now the point is, we are looking at dissolving NiOH twice in a 0.1 molar NaOH solution, right? This is a classic example of what you call as your common ion effect. OH minus is already present in solution, which is going to reduce the ability of NiOH twice to dissolve, right? So solubility product and common ion effect is the broader concept involved out here, right? So like for example, if you are, let's say for example, looking at lead chromate, right? So we have PbCrO4 giving you Pb2 plus chromate ion, right? So this is what is happening when there is like some bit of solubility that is happening, right? So what did I do? I am like adding your K2CrO4, right? So which means I am from my end adding some chromate ions into the solution, right? So which means that obviously it will lead to some precipitation of lead chromate. Why? Because what I had originally was let's say a saturated solution of lead chromate, right? So saturated solution of lead chromate, you can even see why saturated, because you can already see precipitate downstairs, right? At the bottom of the test tube, you are already seeing some yellow deposition, which means it was already saturated. Whatever is soluble is already there. If you add CrO4 to minus from the other end, what will happen is that you are adding your product, right? So if you are adding a product, what will happen? The reverse reaction will take place, right? So reverse reaction takes place, which means PbCrO4 will be found, more precipitate will be found. So similar thing is what is happening here, though not entirely similar, because we are not speaking about an upfront available NiOH twice solution. We are taking taking a 0.1 molar NaOH solution, and we are like, okay, let's see how much NiOH twice can dissolve, right? Okay, we are looking at a sparingly soluble salt and a soluble salt comparison here, right? What do you mean by a soluble salt? Soluble salt would mean that there is a high possibility that whatever amount you add will probably get dissolved. So if you take some n moles of this AX thingy, right, which is a soluble salt according to what is given here, that n moles, initially A plus X minus is not there. The n moles are going to entirely dissociate and go into solution, and we'll get n moles of A plus and n moles of X minus, right? This is what happens in a soluble salt. On the other hand, if I have a sparingly soluble salt AB, if I take some n moles, originally A plus B minus was in there, but now the number of moles that dissociates out of this will be a very small quantity. Let's call it as S, right? So let's say S moles dissolved out of this. So the remaining N minus S is going to be in precipitate form. Remember the lead chromate already remaining yellow thingy, right? Which was there in the beginning. That is this N minus S, and we will get S moles of A plus aqueous and S moles of B minus aqueous in your solution. This S, number of moles that dissolves per liter, if we had, let's say, 1 liter as my sample, the number of moles that is dissolving per liter is what you call as your molar solubility, represented by S. At some places you will see capital S, at some places small s, but it's not ambiguous, right? Whatever it is, S is what we take as our molar solubility, number of moles of your solute that dissolves per liter of solution. This is our sparingly soluble salt molar solubility. Now what is KSP? KSP is solubility product, just like how we take different ions and like how we speak about product of different ionic concentrations and all. That is your solubility product. Solubility product is specifically A plus concentration into B minus concentration at equilibrium, as in it has to be a saturated solution. I mean, if I add a little bit of this sparingly soluble salt, and if I still can add more of this which will dissolve, then it won't be called KSP, right? So in a saturated solution, A plus into B minus is what you will call as KSP. This is for AB type molecule. If it was A to B, it will be different. 2A plus and B2 minus will be there. So A plus concentration square will be there, B minus will be there. What we have seen in equilibrium chapter in the beginning, when we speak about equilibrium constants, same kind of story is what is happening here, right? So A plus into B minus, right? So let's say that I'm looking at the equation and I write Okay, I'm getting A plus plus B minus. If I want to speak about the equilibrium constant, it is supposed to be A plus into B minus divided by activity of AB, and AB being your pure solid, whatever remains, whatever is not dissolved, right? So most of the ionic salts are what we consider as strong electrolytes, right? In the sense that they will have 100% dissociation in solution, right? So irrespective of the quantity, they will have 100% dissociation. At least whatever it dissolves will be 100% dissociated unless specifically mentioned in question, right? So there are partial salts with partial covalent character where dissociation might not be 100%, but yeah, generally we assume 100% of all soluble salt will be in dissociated A plus B minus form, and obviously activity of AB, which is a solid, is a fixed value, right? So you might have studied, we take activity of solids and liquids as 1. The idea is, it's not taken as 1, the idea is that it is a fixed value. So why like unnecessarily carry around a fixed value? Let's take it to the other side. So we'll get K equilibrium into AB solid activity should be equal to A plus into B minus. Now since AB solid activity is a fixed value, this is also going to be a fixed value, which we call as KSP. This is the idea of what we call as solubility product, right? So solubility product constant. Now looking at our particular case here, right? So here we had NiOH twice, which we are trying to dissolve, and I am getting Ni2 plus rather plus 2OH minus, right? So let's say some amount I took, I don't care. From that, let's say some C was the initial amount, let's say that I took. Some S moles dissolved, right? So at time t equal to 0, I just had C and no Ni2 plus, no OH minus. OH minus was there, 0.1 molar was already there, but yeah, whatever. So let's say t equal to T1 or sometime t equal to T, it has become C minus S. Let's say in 1 liter, S moles have dissolved of NiOH twice. So I'm going to get S moles of this. From 1, I'm getting 1 and 2. So from S, I'm going to get S and 2S. Right? Now, the thing is that as far as OH minus is concerned, I'm getting 2S concentration of OH minus from my NiOH twice. But the point is that NiOH was already, OH minus was already present in solution as 0.1 molar. NaOH is a strong base, 100% dissociation. So 0.1 molar NaOH means 0.1 molar Na plus and 0.1 molar OH minus. So this OH minus was already 0.1 molar. So this equilibrium will be shifting backward. You might have heard common ion effect, right? So if I add a product, reaction will go in the reverse direction. Similar Lee-Chatelier principle idea. Right? So what we can say is that what this means is that OH minus is already present. OH minus from your NiOH twice can be neglected. 10 to the power minus 15 equilibrium constant. This is not even equilibrium constant. KSP is 10 to the power minus 15. This is a small value that I'm going to get. If only NiOH twice was present, I would have said, okay, S into 2S whole square should be equal to 2 into 10 to the power minus 15. From here, I can say that S cube is equal to 1 by 2 into 10 to the power minus 15, which means S is roughly of the order of 10 to the power minus 5 molar. If only NiOH twice was present, then I would be getting solubility roughly around 10 to the power minus 5 molar. But if that was the case, OH minus would have been 2 into 10 to the power minus 5 roughly, right? But 2 into 10 to the power minus 5 molar is 0.00002, right? 4 zeros and 2. And this is already 0.1 molar available from NaOH. Obviously, this 2 into 10 to the power minus 5 can be neglected. No. So we can say that even if NiOH twice was alone, even then the OH minus would have been so low. So because of already existing 0.1 molar OH minus, this equilibrium is going to further shift backward. OH minus I get will be way lower than this 2 into 10 to the power minus 5. So I can ignore this 2S in comparison to the 0.1 molar, which is already present in the solution. So here, what will I get? KSP is always supposed to be this value, 2 into 10 to the power minus 15, and that is going to be equal to solubility into 0.1. This is the idea, right? So I just hope it was already 0.1 or 0.01. What was it? Yeah, 0.1 molar only. So NaOH being a strong base, there is 100% dissociation, no reversible arrow, right? So 0.1 molar would mean that this was originally not there, but now 0.1 molar is there. So in this 0.1 molar, your solubility of NaOH twice will be even further reduced. We can say total OH minus will be approximately 0.1 molar only. The 2S that is coming from NaOH twice can be ignored. S is the molar solubility, as we have already discussed. Going forward, what will I get? In our saturated solution, we know any product is supposed to be equal to Ksp. So we will be getting 2 into 10 to the power minus 15 is equal to S into 0.1 square. Wait, I think I did not take square here when I wrote that equation. So let me change that. Yeah, so S into 0.1 square, right? So Ni2 plus into OH minus concentration square. So we are getting 0.1 square. Right? So what do we know? We are getting this S to be equal to how much? We will take this 0.1 square to the other side. We will get 2 into 10 to the power minus 15 divided by 0.1 square is 0.01, right? So 10 to the power minus 15 divided by 10 to the power minus 2. When it goes up, it will become 10 to the power plus 2. We will get 10 to the power minus 13 remaining. So our solubility turns out to be 2 into 10 to the power minus 13 molar. Imagine, if it was present alone, it should have been somewhere around 10 to the power minus 5 molar. But now it has become 10 to the power minus 13, which is 10 to the power 8 times lower, which is like 1000 lakh times or 10 crore times lower, right? Why is that happening? Common ion effect. Who is the common ion? OH minus. Where is OH minus coming from? From NaOH. Strong base, 0.1 molar. So high a value that the reaction got pushed back. Their solubility got reduced greatly because of common ion effect, because of Le-Chatelier principle, if you want to look at it that way. And final answer that we got for solubility, molar solubility S, was 2 into 10 to the power minus 13, which is option D. Okay, so we have finished all the questions from physical chemistry. I hope you had as much fun as solving these questions as much as I had explaining them to you, right? So as far as the questions are concerned, you obviously notice something. There were no hefty calculations. Physical chemistry is where we are supposed to see ugly calculations, but none of them were actually very tough to handle, right? Very easy to do calculations. And conceptually also, you might have realized that none of the questions were too intricate or complex or out of the world kind of questions where you just don't know what to do. Nothing of that sort. Relatively simple formula based questions, be that from kinetics, be that from your any place. I mean, any of the question that you came across, none of these were too tough, right? Simple questions, even like simplest of them would be like the atomic structure question, where you are given the symbol of an element and you are asked protons, electrons, neutrons. This is not something that you would even expect in 10th standard. That is the kind of question that was asked in NEET, right? So none of the NEET papers are supposed to be that tough. So whenever you're preparing, just see to it that you do the fundamentals very clearly, the basics very clearly. Don't fool yourself. Don't try to just by heart things that you don't understand. There is a logic behind everything. If you are going to school, it is entirely possible that school teachers might not explain all of these things to you because there is time constraint in school. They have to do all dance competition, debate competition, but of course there is like time constraint that is there, so there might be a lot of things that are not explained in too much detail. But as a student, stay inquisitive, stay curious, start loving learning, right? So when you start loving this process of understanding and acquiring knowledge, you will understand that you can't just skip over things and be casual and assume that okay, maybe this is true, let me by heart. There are a lot of things that you will have to by heart, no doubt. In chemistry, in inorganic, organic, there are a lot of things that you will have to by heart. But the thing is that there is a logic behind it as well. It might be very complex to go down to each individual concept and explain all of the things behind it very beautifully. But for an inquisitive mind, if you search around, you will get enough things. Even BYJU'S, we provide lots of content where you can find out these different things, these unique things, which is normally not taught everywhere, right? So at least in our paper, NEET 2020, there were no questions from physical, which was out of the world and which required a lot of information. more or less what is taught at school level was what was there. Maybe 1 or 2 questions you had to probably think a little bit for yourself, right? So anyways, this is Abhilash signing off. See you soon. We'll be looking at the remaining questions also from organic. But for now, we have done with Physical Chemistry 2020. See you. Best of luck.